Hello again. This is Math 1120 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Bayes' Theorem and such. And we're going to introduce our discussion of Bayes' theorem, talking about a problem we had before with the urns, and here's the statement of the problem, and there is the diagram that we have. But now we're saying, suppose that a black ball was selected. What's the probability that the black ball came from? Urn 1. Now, from all of these pictures and everything, we can see that there was a 1/3 and 2/3 chance of getting urn 1 and urn 2, and the probability of getting a black from urn 1 was this, and the probability of getting a black from urn 2 was this, and we can compute the total probability of the black by adding this number and this number together. And that's the total probability of the black, because this state of nature is disjoint from this state of nature. Okay, now the question that we're asking though is, what's the probability of U1 given that we know that it is black? So we have a conditional probability rule that we have this way. Now we're using the new notation of intersection now, but that really is just a change in the notation, not in what it means. And so that means that this numerator is going to be this by the general multiplication rule. And the total probability of B is either I got there through the top route or through the bottom route. And so the probability of B is going to be this, the numerator is going to be that. I put all those things in, I can substitute and do the calculation and get this. So the probability that a randomly selected black ball came from urn 1 is 0.481. And that's what Bayes' rule says in general. So suppose A1, A2, A through AN is a partition of the sample space. Then for any event E for which the probability of E is greater than 0, the probability of event A sub I given the event E is this expression. Now, this is kind of a formidable formula. It does exactly what we were talking about, but again, I would suggest a lot of times just draw the picture. Let's look at another example. This example is dealing with unemployed women. So according to a census, 27.3% of U.S. adult women have never married, and so we just call them single. 49.8% are married, and the balance, 22.8%, are either widowed, divorced, or separated, and we just call this category other. So of the single women, this is additional data, 6.7% are unemployed. Married women is 2.6% are unemployed, and the others are 4.9% are unemployed. Suppose that a randomly selected U.S. adult woman is unemployed. What's the probability that she is single? So we go through and we define the events. We list it this way. We're not drawing a picture, but you could draw a picture. So we're listing them this way. The probability of being single, married, and other come straight from the census. And these are the employment figures. And we can figure out the probability of being unemployed by doing a total probability calculation. And so that can be 0.042. Now we wish to determine the probability that a woman is single given that we know she's unemployed. So we want to determine the probability of S given U. Well, the probability of S given U is this by the definition of conditional probability, and by the definition of the general multiplication rule, the numerator is this, and the denominator is going to be that total probability calculation, and this is the calculation we do, so it is 0.436. You should make sure you can complete these calculations because that's good practice for you. we say, and these are some fancy words, we say that the probabilities P sub AI are the a priori probabilities. These events exist prior to any knowledge regarding what happened. However, the probabilities P of AI given E are called a posterior probabilities because they're probabilities computed with some knowledge about the event that happened. So for example, here, you're saying, oh, they're employed, or event E happens. Okay, so that changes things. Notice that the information that Bayes' rule gives us, without any knowledge of the employment status of a woman, there's a 27.3% likelihood that she is single. But with the knowledge that the woman is unemployed, the likelihood of her being single increases to 43.6. So, a priori probabilities are computed prior to any knowledge, and posterior probabilities are computed after gaining some knowledge. Let's do another example. So persons are classified as work disabled if they have a health problem that prevents them from working in the type of work that they can do. And so here is a table showing you the proportion by age of Americans who are 16 years or older who are working disabled, that are work disabled, excuse me. And so we get those. Now, either you're in this set, this set, this set, this set, or this set. So you see these are disjoint events, and that's important for the problem. So if we let M represent the event that a randomly selected American who is 16 years or over is male, then the census probabilities can be listed this way. Probability that you are male, let's see, given that you're 16, and so this is new information, but this tells you, what fraction of the folks are male in the different age groups. So the question that's being posed is, if a work-disabled American age 16 years or older is randomly selected, what's the probability that they are male? And the second part is, if a work-disabled American randomly selected is male, what's the probability that he is in the youngest bracket? Actually, it's not the youngest bracket, it's the second youngest bracket, the one that's called A2. Okay, well, for part A, we're just going to use the rule of total probabilities. So you see we have all these disjoint brackets for them, and they add up to be the population that we're talking about. So the probability of male is the probability that you're male in A1, probability you're male in A2, male in A3, and you just add them up. They're disjoint, and you do that calculation. Now, if you do that calculation, you will get 0.477, and you again should check that you can do that calculation. But then we're going to use Bayes' rule to compute the probability you were in A2, this category, given that you are male. And so that's going to be this. We calculated this in part A, and we have this information here, and so we calculate that. And so the answer to this, when I calculate this entire figure, is 0.104. And you see that in this case, the prior probability and the posterior probability aren't much different. And that means that the individual being male does not yield much information regarding the age of the disabled person. A little bit, but not much. Okay, let's have you do some problems here. This is a problem drawn from your textbook. This is problem number 29. You know what to do. Let's see how you did. I repeated the problem over here so we can see it. Here's the picture that you draw, and I encourage you to draw pictures. So the probability that you have a black are you add this one and this one together. So those are the states of nature. And these are going to be 1/2 times 5/12 and 1/2 times let's see, that was supposed to be yeah, that is a 6/14, that is right. And you get this as your calculation. So that is the answer to part A. What's the probability that it's black? That's a total probability. So you're saying going here and going here. Now determine the probability that it's black using the rule of total probability. And that's, well, we'll get the same answer. And you see the picture will give you the same answer as this. C, suppose the ball is black. What's the probability it came from urn 1? So this is the path you go, and that is going to be 35 over 71, which is this. And then D, suppose a randomly selected ball is red. What's the probability it came from urn 1? Well, there were no red balls, so that's going to be 0. And if you got a red ball, the only way that could have happened would come from urn 2. So those are the answers that you would have for those questions. Here's a problem 31, again a different setup, and you know what to do. Let's see how you did. Again, here's the statement of the problem, and here's the picture that you draw, okay? So we're going to determine the probability. That's a total probability, the probability that it is black, by drawing a tree diagram. So we drew the tree diagrams. And you see here, if you're black, you're in this state of nature, this state of nature, or this state of nature, and you're never in more than one of those. So you're in this one, or this one, or this one. So we are going to figure out what those probabilities are, and we're going to take, this is going to be 1/2 times that, and this one's going to be 1/3 times that, and this is going to be 1/6 times that, and that's what we get. Now, you can also use the law of total probability, and that's just using this in symbols, but you see you do get the same answer. In problem C, if a randomly chosen ball is black, what's the probability that it came from urn 1? Well, you're going to take this probability divided by the total probability that it is black, the way we've done several times, and you see here we will get that this is 0.6110. And part D asks, if the randomly chosen ball is red, what's the probability it came from urn 1, urn 2, and urn 3? Well, it's going to be 0 from urn 1, from urn 2, well, yeah, that's where we're 0 with that. From urn 2, we do the calculation using the figure or otherwise, and we get this. And from urn 3, it is this. And of course, these add up to 1 because this was a 0 probability, and we told you that we were talking about the probability was it was a red ball. Here's another problem dealing with color blindness. Color blindness means you can't distinguish between red and green. You might say, oh, that means you can't drive. Well, no, you can tell light, and so you're okay with that. This strangely happens relatively frequently with males, but not very often at all with women. And here's some information from the census about how many Americans are male and how many Americans are female. So what's the probability that a randomly selected American is colorblind? That's a total probability. And what is the probability that a randomly selected American who is colorblind is female? That means, what's the probability they're female given that they're colorblind? You know what to do. Let's see how you did. Okay, so probability you're colorblind is you do this calculation by the law of total probabilities. Again, you could have drawn a picture if you wanted to. And you get this as your final answer. Now this is Bayes' law of the probability given that you're colorblind, that you're female. Probability you're female given that you're colorblind. And we approach this the same way we do before, and we get this as our answer. A final example. So we're given this data about educational attainment. And so now you fall into one of these categories. So this is a partition of a set. These are disjoint subsets whose union is the entire space. These probabilities will add up to 1. Okay, so if we let M represent the event that a randomly selected American who is 25 years or older is male, then we have this information for those categories. So again, this is more census data, and these are the conditional probabilities. So we're to find what's the probability that a randomly selected American 25 years of age or older is male. That's a total probability. What's the probability that an American male 25 years or older has an advanced degree? And C, what is the probability that an American male 25 years of age or older is not a high school graduate? These are the kind of problems that I could ask you on some assessment. So you know what to do. Let's see how you did. Okay, so here is your approach. You're splitting this up and adding these up with the law of total probabilities, and you get an answer to part A of 0.499. For B, given that you're a male, what's the probability that you're in A6? Well, that's going to be the probability of A6 intersect M, which is this by our general multiplication rule, and divided by the total probability that we found up here, and we get this as our answer. And if we change it, what's the probability that you're in A 2 given, I can't see if that's a 2 or a 1. It looks to me like it might be a 1, but anyway, this is the answer to part C, and it is 0.1232. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.